Look at this curve. Some points are can be important, giving particular high value on particular interval at particular point. So it's good. It's good if we could know them or characterize them. Maybe this part we can see the curve, but if your curve is given just by formula, you would like to know where they will be located on the whole of the domain of the function. So this is our purpose. First, we will define what do we mean by maximum and minimum. So if we look at this curve, we see this is higher value compared to this one. So there, this one seems higher, but there is another one level where the y is higher. But still, here we have an information that means it says that the function remain larger on this interval. Here also remain larger compared to other some x's on some interval. These small mountains, we call them local maximum. Okay, so the small mountains we call them local maximum. So this is this. So we have this one, at least this one, and this one are local. We call them local maximum. Here, these points, if you look at this one, this level, so we see f remain, the value taken is smaller compared to the others on small interval. So this one, this point, and this one also, we call them local minimum. Local minimum. Okay, so it's locally, it's not because for example here we still have higher value, we don't have the whole graph, the global graph of our function, so maybe there are other points or higher or smaller. Here for example f takes smaller value compared to this one. Okay, so here that's why we will first give the definition following space, say what is a local point, global maximum, global minimum. Okay, so the definition so we will say okay that f that x0 is a local minimum, a point x0 is a local minimum. We will add respectively maximum if and only if you can check this comparison, make you can, if you are able to make comparison. So for example here local minimum, this is your x0, you will say that if you have the value taken by f at x0 remains less than the fx for any x in small interval x0. Okay, small interval okay, centered, okay, at x0 for example, centered at x0. Okay, for the respectively for the maximum we should have the inequality fx0 greater than. Okay, so I just need to add the, instead of writing everything here, so let's write just greater than the comparison. Okay, remain bigger than the other values. So this is about local point. Okay, now if we want it global, is a global, sometimes we say global or absolute. Absolute minimum. Okay, minimum. So respectively maximum, global or absolute maximum, if and only if you can check that fx0, so global less than fx, okay, respectively greater than, okay, for any x in the domain. Of course, you need to check the definition for globally. Okay, so this is the two, those are the 2 points you need to know to make the distinction between the two words, local and global. So now it's clear. Okay, so let's so just practice to have an idea about these points. Sorry. So here I prepared these graphs. So let's identify whether we have a local minimum, local maximum, global minimum, or global maximum. So if on this line, we can't make the comparison of x0 at particular x0 with the other values taken. Each time you choose an x0, you fix an x0, okay, an x0 here. You are not able to make, there are values that are greater taken, okay, to the right to x0 that are remain greater than fx0, points x's to the left to x0 remain less than greater yes, less than fx0. So you can't make this comparison on centered interval, so there is no local points, no local extreme points, extrema. Okay, are there global ones? No. The points on my curve takes y's, the y's taken are remain large, okay, very large and positive, and take large negative values. So we have no local also, okay, no global extrema. Okay, none of them. Okay, so you see it's possible to have none. Okay, now let's see with the parabola y equal x2. I see that I can compare at 0. 0 remains the smallest values. I can compare it locally, and for x on the interval, for example, -1 and 1, the fx remain greater than f0. But I can do the comparison everywhere on the whole interval r. On the whole interval r. So yes, I have 0 is the minimum point. So I can say the minimum, I can write that the minimum of x2 on R is f0, which is 0, and it's local. 0 is local. Okay, no maximum. So the maximum. So let's correct this one. Okay, I can say that maximum of x2 doesn't exist. Okay, maximum of x2 over r doesn't exist. Let's write it here. So maximum of x2 on r do not exist. 0 is the only local minimum. Okay, no other local maximum. No local maximum. Okay, so now we have this curve. This is y equal x3. Okay, here also it behaves like the line. Okay, like the line here. So the y's take large values. Okay, non-stop. The y's also take large negative values, so no global maximum. Okay, no global points. So no global, and there is no local also. Locally I cannot make a comparison, so none. no extrema about extrema, no extrema, local or global. Now let's look at the sine function. This is the sine function. This is y equal sine x. So you see that you have small mountains, some small valleys. So the mountains means here I can make the comparison. fx remain greater than the other y's corresponding for x's on small interval. Okay, centered at this point. So I have several infinite number of local extrema. Okay, so we have it, and we have infinite number of extrema, minimum and local and global. Okay, they are at the same time local and global. Okay, and we can exactly write the following. We have minimum of sine x over r. Okay, we have the smallest value is -1, but it is taken, it's taken at all the points that are they are like pi, no, not pi, pi over minus pi over 2 plus a multiple of pi. Okay, the maximum of sine x over r, okay, will be 1. Okay, so it's 1. Maximum over r is takes the value 1, and it's attained at the points like angle pi over 2. For example, here I have so it's not the sine function. X equals 0. No, it's cosine function. It's okay, let's correct this. So it's not the sine function. I thought it was the sine function. Okay, no problem, we will correct this. Okay, let's correct this one. Yes, we said it's cosine function. Cosine at 0 is 1, at pi over 2 is 0, at pi it's -1, so it's cosine x. So the minimum of cosine x here is -1, the smallest value, and it is taken at cosine of pi plus the multiple, and the maximum is 1 and is attained at 0, so it's cosine of multiple of pi, 0 plus 2n pi. So you see now that anything can happen, and it is useful if we are able to identify the location of these points. So this is the next thing we will do. So the first theorem that will help us for solving the found extreme values is called the theorem the extreme value theorem. Okay, so let's write it here, extreme value theorem. Okay, so let's write it here, extreme value theorem. So from now on we will use the abbreviation UVT. Okay, so the theorem says the following. It says the following: if you have f continuous, f c0 on an interval EB, okay, then the maximum EB is closed, so EB closed bounded interval. Okay, so then the maximum of f and minimum of f is attained somewhere on the interval. Okay, so there exists an xm, at least one, not necessarily only one, in the interval EB, such that fxm, okay, will be the minimum will be equal to the minimum of f over the interval EB, and fx capital M will be the maximum of f over the interval EB. Okay, so this is our theorem. Okay, so this is our theorem. We will not prove this theorem because it uses tools, so that advanced tools of analysis, but we will use it. You will see. But before that, we will need the following, the other theorem. Let's write it in green. Okay, so the other theorem is the Fermat's theorem. So here it is what it says. The Fermat says the following. So if we have a function f defined on an interval containing x0, f, a function, okay, defined on an interval containing x0. Okay. Then f has a local extreme point at x0, then it's a critical point. x0 is a local extreme point of f, then x0, then I will give the answer, not like that. Let's express it differently this time. So I will say, okay, so we will say two situations can happen. Either f is not x0, either f is not differentiable, at x0, or if f is differentiable, then f prime at x0 necessarily is 0. Okay, and this kind of points, we say also the theorem is expressed differently. We say x0 is a local extreme point of f, then x0 is a critical point. So either one of those conditions, when it is satisfied, x0 is called a critical point. Okay, is critical point. So this is what the theorem says. Okay, so yeah, this yes, theorem says that if my function has a local extreme point, necessarily my point is on a critical point. A critical point means f is not differentiable at this point, or that if f is differentiable, necessarily f prime at x0 is 0. Okay. So, for example, maybe start by an example. Why not? An example. Let's say fx equal x2. Okay. So f is differentiable everywhere here. F is differentiable. We know it's a polynomial function differentiable on R. Okay. So if I'm looking, the theorem says if you are looking for a local extreme point, there must be a critical point. That means where f is not differentiable, or f prime at x0 equals 0. Okay, so let's solve f prime of x. So I solve it. 2x equals 0 if and only if x equals 0. Good. Yes, so I found 0, and we see that 0, yes, it is a local minimum. Okay, 0 is the local minimum. We saw it from the graph. Okay. Okay. Now look at the other example. What if you take fx equal x3? F also is differentiable everywhere on R. Okay. The derivative, if you take the derivative, it's 3x2, solve the equation equals 0, you will get again x equals 0. So, but then here there is a problem. We said there is no extra point here. Okay, we said there is no extra points, no extrema for the curve y equal x3. So what is happening here? Where is the problem? There is no problem. There is no problem because the theorem doesn't say that we have. The theorem doesn't say. Okay, the theorem is not saying that you have the local extreme point. It says they are candidate. Your candidate must be among these points. Okay. For example, here 0 is not a local extreme point, but is solution of f prime. Okay, so this is just Fermat's theorem reduces for us the domain of search. It limits us to look to among the critical points. Okay, the candidates for optimality are among the critical points. So there is just, yes, which is not of course which is important result. Okay, and an application now. Yes, what it says also, so this is the remark. Let's put this as a remark. Okay, as a remark, important remarks here. So Fermat says to look for the candidates, the candidates for local optimality among the critical points. So we saw an example. Okay. Okay, so this is very, very important because it gives us a way to solve some category of optimization problem. Okay, so here is the method of the closed interval So what do we mean here? We mean that we are able to find the max and the mean of f over how to find, so max or mean of a function over a closed interval. So we have the method. The method says that, so the first, the extreme value theorem says you are sure that we have a maximum and minimum. Okay, we have them. They exist. They exist where? Here, somewhere on the interval. So either at E or B, okay, or at the interior, or between E and B. Okay, so but when they are interior, that means they are local extreme points. Okay, they will be local if they are okay. They may be local extreme points. Yeah, because we want the maximum minimum. If they are inside, they become also local and minimum. So that's why the method consists on finding first local extreme point. So find local candidates, critical points, anterior critical points. Let's express it like that. Okay, find local extreme point, critical points. Okay, Okay, that means depending of your function is differentiable or not, they are here. Okay, they are satisfying either f not differentiable, you regroup all the points where f is not differentiable, and where it is differentiable, you solve the equation f prime x equals 0 and you regroup these points. Okay, and then the evaluate fe fb, evaluate fe fb, and then compare. Okay, so usually what I do, I prefer to put it in a small table like that. I put my x, I put e, I put b. Here I put the critical points, and here I evaluate fx. So I have fa, I have the values at the endpoints of the interval. Okay, and then I compute the values at the critical points p. So suppose that we have x0, x1, etc. Okay, so I will compute fx0, fx1, and etc. Then then I will compare, and the maximum of f over the interval ab will be obtained by taking the maximum of fa of all those values, fx0, etc., until fb. Okay, and the minimum of f over eb will be also the minimum of all those values. Okay, so we have method that controls, we have control on such category of problems. Okay, for this family of problems we know how to proceed. Of course there is a difficulty when finding critical points, because we have to solve an equation f prime x equals 0, which is not always easy. We know how to solve first degree equation, higher degree, second degree polynomials, second degree we have control, third degree it depends if we can factor or not, fourth degree also, etc., etc. So the problem is not easy, but we have a method and we know that it exists, we have a solution. Okay, so yes, great. Let's now do another example here, then just applying this method. What if I ask you to to find the maximum of cosine x, the function, over the interval, let's say minus 2 pi up to 2 pi. Okay, let's do that. So let's make bigger the graphing here. Let's put it bigger and close and solve it. Okay. Okay. I'm not able to do it. So let's do that. Okay. So what are the let's put our table, because we can see the critical points. The anterior critical points, the endpoints are minus 2 pi and 2 pi. Okay. So maybe I need just to use another color. Prefer choose the dark one. Okay. Now I'm good. Okay, here is the graph. Okay, so let's put our table here somewhere. So the endpoints are minus 2 pi, 2 pi. Okay, endpoints minus 2 pi. Here is 2 pi, minus 2 pi. They are not interior as long because I don't have points the other side. Okay, so they are endpoints. Then here, so you will have 0 as critical point we have, because they have tangent horizontal here, horizontal here, here. That's all. So I have 3 points. So 0, 0, pi, minus pi. So I have minus pi, 0, and pi. Okay, this is x. Now cosine x is here. Cosine minus 2 pi 1, minus pi minus 1. Here it's, yes, minus 1. At 0 it's 1, minus 1 and 1. So you see, so I can answer the maximum will be 1, and it is attained at it's a cosine minus 2 pi equal cosine of 0 and equal to cosine of 2 pi. So it is attained at 3 points, the maximum points. Okay, so this is what we learned today: local extreme point, critical points of function, Fermat's theorem, and extreme value theorem, and the method of the closed interval. Okay, so this is also the first time also we are solving optimization problems. Definition also of local extreme, absolute extreme value are very important.